Here's where we ended last time, where we see the smaller pKa value on acetic acid, and that tells us it's the stronger acid. We say the only reason that is due to this conjugate base being stabilized by resonance. We say it can delocalize its charge. We say that any time a chemical species can delocalize the charge, it's more stable than up here. The negative charge just has to stay there on oxygen. So there's this thing called the inductive effect. What is the inductive effect? Electron withdrawing atoms and groups can also stabilize a conjugate base through the sigma bond of the molecule. So that negative charge, if there's an electronegative atom, like here there's a iodide or iodine atom stuck to this carbon. So when this proton comes off, there's that negative charge, it's delocalized. But induction says kind of like a wire a little bit through this bond can stabilize that negative charge. And we see as we put on a more and more electronegative element, fluorine being the most electronegative halogen, the acid is stronger. So fluoroacetic acid, stronger than chloroacetic acid, stronger than bromoacetic acid. And this is what caused chemists to say, how do we explain this? Well, there must be this thing called the inductive effect. So it's a lot of things are observed, and then an explanation is come up with for the observation. So here's this regular old acetic acid, and you can see all of these are more acidic than just normal acetic acid. So putting an electronegative element here can stabilize that negative charge that's moving around on these oxygen atoms by induction.
So the stronger the higher the electronegativity, the stronger the acid?
Except for comparing HCl and HF. That's going across the group with that binary acid. So this is, you gotta relate it to the inductive effect. So instead of just putting on one of these, one chlorine, we go ahead and put on two, and we have twice the induction going on perhaps, and it makes the acid stronger. Then we put three of these things on. We can imagine if we had some trifluoroacetic acid, it would be even stronger than this one here. So here is our alkane, and if I pull off a proton, I have a lone pair of protons here. You can barely see it in the orbital. So it has this negative charge, and here's this large pKa, meaning very weak acid, weakest acid known. That means this has got to be about the strongest base known to mankind. All right, now we come down to ethene. Now we have a double bond. We pull off this hydrogen, leaves two electrons there. I don't know what happened to the negative charge, but it should be there. And you can see it's still a weak acid, but quite a bit stronger than the corresponding alkane. And here, acetylene, pull off this proton, you'll have a lone pair of electrons, negative charge, and a pK that's quite a bit stronger than these others. So it says here, the more S character an atom has, the atom being carbon, should maybe wrote carbon instead of atom. Well, there's other atoms that we could look at. The more electronegative it can be thought to be. So the more electronegative, the more happy it can be with the negative charge. So the more stable this conjugate base is than this conjugate base. Makes this more acidic than this alkane. This alkyne is more acidic than this alkane because this negatively charged species is more stabilized because of the hybridization of this atom. We can say it's more electronegative. And this percent of S character, there's just one S and one P, so it's one S and two P's. So it's 30%. 4 items here, one S. 1 out of 4 is 25%. So our Lewis acid-base definition has to do with electron donators, electron acceptors. A Lewis base can donate an electron pair, and this is why organic chemists like Lewis acid bases, because we form a new covalent bond. Typically involves bond formation, where Lowry Bronsted proton moves around. Now maybe you break a proton bond and form a new one. But here we can form a bunch of different new covalent bonds. A Lewis acid, they're called electrophiles. They want a lone pair of electrons. We say they love electrons. Lewis bases are called nucleophiles. They're looking for the nuclei of an atom. So in the most generic sense, here's a nucleophile, here's an electrophile, and lone pair of electrons, I always say that tells you it's a Lewis base. And here's a Lewis acid. This thing with its positive charge can accept that pair of electrons. So electron donator, electron acceptor, and we form a new covalent bond. Here's the favorite example in the general chemistry books for a Lewis acid-base reaction. And borons, always an interesting thing because it doesn't obey an octet rule. It's an exception, but we say has room to accept those electrons. Here's the new bond that's formed. Now here is something very exciting. We'll learn quite a bit. This here, if you're interested, is called an SN2 reaction. It's a substitution and it's bimolecular. So this thing here, it's substituted for chloride. Here's our nucleophile, and here is what we might call a leaving group. So these electrons slam into this carbon. These electrons leave with the chlorine atom to form chloride over here. And we might even think about this chlorine being electronegative and inducing a little dipole, making a little positive charge on this carbon. So that wants to slam into there. There's the new bond formed. Here's a good example of our Lowry-Bronsted acid-base reaction. Ammonia, common base. There's acetic acid. And pulls that hydrogen on. These electrons jump up on there. So you can say acid base, conjugate acid. The ammonium cation. I hope none of you left your windows rolled down. I hope the hail doesn't destroy my garden. Alright, so that last slide had something exciting. I've mentioned this before. That first mechanism I did here on paper, and you all were supposed to do it as well in chapter 1. What is curved arrow formalism? It shows the flow of an electron pair from the electron donor, the nucleophile, to the acceptor, the electrophile. It slams into there, forms a new covalent bond. These electrons jump off onto chlorine, so it has its full octet. And so curved arrow shows the flow of electrons. The arrow always starts at either a lone pair or a bond. That's where electrons are. So one way to lose points is to start your arrow on carbon and draw it pointed to the electrons. You don't want to do that. Curved arrows always start at electrons and go to atoms. Alright, intermolecular forces. That's why an ideal gas, a real gas isn't ideal. A real gas has an attraction for another molecule of itself. It could be London dispersion forces, could be a dipole-dipole, could be hydrogen bonding. So in case you forgot what an intermolecular force is, it's forces between molecules. An intramolecular force would be a bond, a chemical bond somewhere inside a molecule. But an intramolecular force is forces between molecules. And it explains a lot of things, like boiling points, melting points, and this thing here, which is very important, students sometimes don't like, and that's solubility. How do you know if something's going to be soluble in something else? You look at the intermolecular forces involved, and we have this thing, it's mentioned here in a little bit, which is like dissolves like. So a polar molecule like water, we say has a dipole moment. Water also has hydrogen bonding going on. London dispersion forces, that's on things that can't hydrogen bond and are very nonpolar. They don't have a dipole, like propane, methane, argon gas. The only intermolecular force argon gas has is a London dispersion force. So solubility, like dissolves like. That means polar solutes will dissolve in polar solvents. Nonpolar solutes dissolve in nonpolar solvents. So if we have molecules with similar intermolecular forces, they can mix freely. So here might be something like sodium and chloride, like a crystal of sodium chloride. And we say sodium chloride's an electrolyte. You dissolve it up in water, and you get these ions. Solution conducts. How is it that these ions get dissolved in water? Well, since oxygen's very electronegative, hydrogen's not so much. We have a little dipole arrow that way and a dipole arrow that way, and they're like vectors. They sum up like this. So here is a cation called it sodium, and we say it's solvated by the solvent. The solvent is interacting with the solute. To bring this back into like chapter 13, Gen Chem, and we say it's hydrated. So here's chlorine. Now it's negative, so the opposite end of water interacts with that, and it's hydrated. And so water is a good solvent for a lot of ionic things. Not every ionic thing is all that soluble, like all the solubility rules, like hydroxides, sulfides, silver chloride, mercury chloride, lead 2 bromide, all those exceptions. A polar solute dissolves in a polar solvent, and sometimes they get cold, sometimes they get hot. Ammonium chloride, you did that and it would always get cold. Calcium chloride gets hot. Sulfuric acid would get hot. I always tell my students, go home and put some salt in a cup, pour some gasoline in there and see if it dissolves. And then I say, no, pour some olive oil in there. So this would be like trying to dissolve table salt with olive oil. The olive oil is very nonpolar, and here's like salt, and there's no interaction. So the intramolecular force, which is lattice energy in this case, is pretty strong. And this is just London dispersion here holding these things together. And of course, pretty easy to pull these solvent molecules apart because the London dispersion force is smaller of them, but these don't want to break apart. The solvent cannot break apart the intermolecular interaction of the solute, so the polar solid will not dissolve in the nonpolar solvent. Now here's a nonpolar solute in a nonpolar solvent. This might be like your sour cream in your olive oil, your butter in your olive oil, your whipped cream in your olive oil. That sounds tasty. So notice this is a hydrocarbon, just a long chain hydrocarbon. Here's a nonpolar solvent. Well, here all the intermolecular forces are kind of weak. So this is probably like your butter. Maybe this is your olive oil. One's a liquid, one's a solid. But it's the weak intermolecular attractions of the nonpolar substance are overcome by the weak attractions for a nonpolar solvent. The nonpolar substance dissolves. So here's your Italian dressing. You got your olive oil and you got your vinegar, which is mostly water, 95% water, 5% acetic acid on. This is why water has such a high boiling point for its low molecular weight. It's off the charts. 100 degrees Celsius, thing only weighs 18 grams per mole. And so the olive oil doesn't dissolve very well, so you shake it up and you make an emulsion and put it on your salad real quick and eat it, and then by the time you grab it again, it's separated. So nonpolar substances do not want to dissolve in water. So they're very unlike each other. Like dissolves like. So you've heard me use the name hydrocarbons. Hydrocarbon means just carbon and hydrogen only. And we have some way we can classify these things. First up, alkanes. So when it ends in ane, that means all the carbons have single bonds, which means they're all sp3 hybridized, and we have that ane suffix. Alkanes have no functional group. What is a functional group? A functional group is a part of the molecule where reactions occur. So as I said in the past, alkanes are relatively inert. They're not really acidic. That's why that pK number of 50. There are reactions, and we'll study them, but for the most part, an alkane, well, the combustion reaction can make an alkane undergo a reaction, but not a lot of easy little reactions we might do in a flask. And then, of course, a cycloalkane is when we have a ring. If it ends in ene, that means we have an sp2 hybridized carbon in there, most likely two of them, to form a double bond. Double bonds are represented in a molecule, and we can cycle them. An alkyne has a triple bond, and aromatic is a special class of ring. So here's CH4, methane. Here's CH2, CH6. So we can see these aren't condensed formulas. These are just the molecular formula. Methane, ethane, propane, butane, and then we got something going on. These first three have no constitutional isomers. How many ways can you connect one carbon? You can't. Two carbons, you can connect them together, and that's the only way you can connect two carbons. If you have three carbons, somebody might say, well, can you connect three carbons into a triangle? I guess you can, but we'll talk about that when it comes up. Cyclopropane. Doesn't exist in nature. Only made in the lab by man. So in nature, these first three have no constitutional isomers. But as soon as we get to butane, we can take this carbon off the end of the chain and attach it to this middle carbon, and then we have this thing called isobutane. So isobutane and butane are what type of isomers? Stereoisomers, true or false? It's got to be false. I'll make a joke. Are they patriotic isomers? What's a patriotic isomer? Constitutional isomer. All right, so constitutional isomers have the same molecular formula, but are connected up differently. You see a straight chain here, and a shorter chain and a branch. So butane and isobutane are constitutional isomers. All right, so here's pentane. 1, 2, 3, 4, 5. Here's some tricky way of denoting pentane. All right, if we chop one of these off the end and stick it there, we have this thing called isopentane. And notice we might see a similarity here. Isopentane, isobutane. Iso anything, like if I had isoheptane or iso-octane, the iso would mean the second carbon in on the chain has a methyl group, and that's about it. And after isobutane, I don't think using the word iso is that important. And of course, so pentane has 3 constitutional isomers. We have 5 carbons, and they're all sp3 hybridized. There's only 3 ways we can connect them. Straight chain, 1 carbon shorter with that carbon stuck on the second carbon. Notice same thing here. 1 carbon shorter, stick that carbon we just cut off on the second to the end. So they're both iso. So here's isopentane, isobutane. This thing here is just a novelty, I think. Neopentane. Alkanes do not have a functional group. I'm beating a dead horse. right now. What is a functional group? The region of atoms in a molecule with distinctive chemical properties, regardless of the other atoms in the molecule. The atoms of the functional group are linked to each other and then to the rest of the molecule by covalent bonds. So some of our chapters in this book are on different functional groups. A double bond is a functional group. A triple bond is a functional group. An OH, an alcohol, is a functional group. It has certain properties, meaning it does certain chemical things, certain reactions. I guess I doubled up on that. So you want to learn to count in organic chemistry: meth, eth, prop, bute, pent, hex, hep, oct, non, dec, undec, dodec, tridec, tetradec. And then if I put the word ane, we got methane, propane, all those good things. Tells us the number of carbon atoms. Now here is a beautiful thing. For any alkane, it's going to follow this formula here. If we know the number of carbon atoms, if we double that and add 2, we'll get the number of hydrogens here. So 1 carbon atom, N equals 1. Okay, 1. 2 times 1 is 2 plus 2 is 4. That wasn't too exciting. Let's go to heptane. Here's 7. 7 twice is 14 plus 2 more is 16. Well, let's do 13. I got 13 carbons. How many hydrogens do I have? I'm going to go 13 twice is 26 plus 2 more is 28. Now there you go. So when I see a chemical formula, the first thing I do is I do this in my mind, and when I see less hydrogen than what's there, I say, what's going on? There must be double bonds. And so by the end of the semester, I hope you'll do the same thing. Whenever you see C4H8, you're going to say, ooh, is that butene or cyclobutane? All right, I'm out of time.